The story of Niels Bohr's introduction of the quantum model of the atom begins at a moment in science when confusion and curiosity were colliding with equal force. The early 20th century was a battlefield of ideas, with physicists struggling to understand why atoms behaved in ways that no existing theory could explain. Atoms were supposed to follow the clean, predictable laws of classical mechanics, laws that had guided humanity for centuries. Yet every time scientists tried to apply those laws to the microscopic world, the results shattered expectations. Something was missing, something deep and fundamental, and it was in this chaotic search for answers that Niels Bohr stepped forward with a bold vision that changed physics forever. Before Bohr arrived with his revolutionary model, the atom was treated like a miniature solar system. Electrons were imagined as tiny planets orbiting a central nucleus, much like the Earth circles the Sun. But this picture, as charming as it was, fell apart the moment scientists examined it closely. According to classical electromagnetic theory, any charged particle that moves in a curved path, like an electron in orbit, should continuously lose energy by radiating electromagnetic waves. That energy loss should make the electron spiral inward, falling into the nucleus within a fraction of a second. If that were true, matter as we know it could not exist. Atoms would instantly collapse. Yet the world clearly did not dissolve into nuclear dust. Something in nature was holding electrons in place, something classical physics simply could not explain. Bohr recognized this contradiction not as a small error in understanding, but as a sign of a much deeper truth hidden beneath the familiar laws of physics. He realized that the atom was not obeying the same rules that governed planets, projectiles, or mechanical systems. Instead, it was obeying a new set of principles that no one had properly defined. The atom was not a tiny solar system, it was a quantum object, governed by discrete, abrupt, and unfamiliar rules. And Bohr took the daring step of rewriting the laws themselves. Drawing inspiration from Max Planck's early idea that energy comes in discrete packets, quanta, Bohr proposed something radical. Electrons in an atom could occupy only certain allowed orbits, each corresponding to a specific energy level. They could not drift continuously through space like planets in the cosmos. Instead, they were locked into fixed, quantized shells. The very idea that nature might restrict movement to fixed energy levels was revolutionary. It was like saying the universe had invisible rails guiding electrons into precise, allowable zones with no freedom to wander in between. This notion was not only strange, it defied all classical logic. But it worked. Bohr's insight breathed stability into the atom. If electrons were restricted to specific orbits where they did not radiate energy, then matter could remain intact. The atom no longer collapsed in theory, just as it did not collapse in reality. This simple but profound rule became the foundation of a new understanding of atomic structure, and it was only the beginning of what Bohr's quantum model would reveal. Bohr's atomic model did more than stabilize the atom. It explained one of the longest-standing mysteries in physics, the spectral lines of hydrogen. For decades, scientists had observed that when hydrogen gas was heated or electrified, it produced light at very specific wavelengths, bright lines of color appearing in dark space. These lines formed a pattern, a code. But no one could decode it. It was as if nature was sending a message, a clue about the structure of the atom, but the key to understanding it was missing. Bohr supplied the missing key. In his model, each spectral line corresponded to an electron jumping from a higher energy level to a lower one, releasing energy in the form of a photon, a particle of light, with a precise wavelength. The atom was no longer a silent, invisible structure but an active, quantum machine releasing information every time an electron moved. Suddenly, the mysterious spectral lines made sense. They were not random, they were signatures of quantum transitions. Bohr had revealed the language of the atom, the rhythm of electron motion expressed as light. This explanation was more than a scientific breakthrough, it was a moment where the microscopic world and the macroscopic world connected in a meaningful way. For the first time, humanity understood that the colors we saw in the spectrum were not abstract patterns, but direct evidence of quantum behavior. It was as if Bohr had handed scientists a new pair of glasses, allowing them to look into the heart of matter and see the rules that governed it. His model did what no classical theory could ever achieve. It offered a consistent, predictive explanation of atomic structure. What made Bohr's contribution so astonishing was not just the mathematical elegance of his theory, but the philosophical shift it introduced. Classical physics was built on continuous motion, predictable forces, and smooth transitions. But Bohr's atom existed in a world where transitions were abrupt, energy was delivered in fixed chunks, and movement occurred through sudden leaps. These quantum jumps, once dismissed as impossible, became the central players in atomic behavior. Bohr forced the scientific community to confront the idea that reality at the smallest scales might be discontinuous, non-intuitive, and deeply mysterious. Yet Bohr's model was also profoundly practical. It gave scientists a tool to calculate, predict, and understand atomic behavior with newfound accuracy. It laid the groundwork for quantum mechanics, the field that would soon revolutionize physics, chemistry, and technology. Bohr had opened a door that could never again be closed. The quantum world he revealed was not a speculative realm, it was the very foundation of the universe. As Bohr developed his model further, he realized that the stability and structure of the atom were only part of the story. Electrons were not simply particles whirling in fixed orbits, they were entities with dual identities, sometimes behaving like particles, sometimes like waves. Although this idea would not be formalized until the work of de Broglie and Schrödinger, Bohr sensed that the quantum world operated differently from anything classical physics had ever imagined. His model was a stepping stone toward a deeper truth that electrons did not occupy definitive paths, but cloud-like states governed by probability. Bohr's early willingness to challenge the deep roots of classical physics set him apart from many of his contemporaries. While others looked for small adjustments, Bohr accepted that a fundamentally new framework was needed. His atomic model was not a polished final answer, but a bold first step into uncharted territory. It was a conceptual breakthrough, a leap of imagination grounded in mathematical consistency, experimental evidence, and philosophical courage. The significance of Bohr's contribution cannot be overstated. His model influenced every major development that followed in quantum theory. Werner Heisenberg built on Bohr's ideas when creating matrix mechanics. Schrödinger's wave mechanics expanded the quantum picture Bohr helped define. Even Einstein, though critical of quantum uncertainty, was provoked, inspired, and challenged by Bohr's thinking. The Bohr model acted as a spark, igniting the most profound intellectual transformation in modern science. As Bohr deepened his research, he also realized that the quantum nature of the atom was inseparable from how we observed it. The act of measurement played a crucial role in determining what could be known. This insight would eventually grow into the principle of complementarity, one of Bohr's most influential philosophical contributions. But even in the early days of his atomic model, Bohr sensed that the observer was no longer separate from the observed. Quantum behavior depended on the interaction between system and measurement, a radical departure from classical objectivity. The story of Bohr's quantum atom is not just a story of scientific discovery, it is a story of human curiosity pushing against the boundaries of reason. Bohr's willingness to embrace the strange, the counterintuitive, and the mathematically elegant allowed him to see possibilities that others overlooked. He did not fear the quantum leaps that violated classical intuition. Instead, he celebrated them as clues to a deeper understanding of nature. His model offered a new way to visualize the invisible world within every atom. It allowed scientists to move from guesswork to prediction, from confusion to clarity. It provided the framework for understanding chemical bonding, atomic interactions, and the mechanisms of light and energy. The periodic table itself gained new meaning when viewed through the lens of Bohr's quantized electron shells. Every element, every compound, Every chemical reaction could now be understood as the result of quantum structure. Bohr's introduction of quantized energy levels was more than a theoretical leap. It was an intellectual revolution that reshaped the foundation of physics. It showed that nature's secrets were not hidden in the smooth curves of classical laws, but in the sharp transitions of the quantum world. His model revealed that the universe was built not from continuous motion, but from discrete steps, each governed by fundamental principles that were as elegant as they were surprising. Bohr's work marked the beginning of a new era. It set the stage for quantum mechanics, nuclear physics, and the technologies that would eventually shape the modern world. Without Bohr's bold step, the quantum revolution might have unfolded differently or more slowly. His vision illuminated the path that countless scientists would walk in the decades to come. Bohr's introduction of the quantum model of the atom is a foundational chapter in the story of science. It is the moment when humanity first glimpsed the true behavior of matter at its smallest scales. It is the moment when the classical world gave way to the quantum universe, a universe full of mysteries, possibilities, and hidden truths waiting to be uncovered. And it all began with a quiet, thoughtful physicist who dared to believe that the world could be stranger and more beautiful than anyone had imagined. As the quantum model gained recognition, the scientific world began to realize just how profound Bohr's vision truly was. The atom, once thought to be a simple sphere or a miniature mechanical system, had revealed itself to be a dynamic quantum structure governed by rules that seemed almost paradoxical when compared to everyday reality. Bohr had done more than modify a theory. He had unlocked an entirely new way of understanding the fundamental architecture of matter. What made his idea so powerful was not just that it explained what classical physics could not, but that it offered a pathway toward the deeper mysteries that lay hidden within the atom. One of the most remarkable outcomes of Bohr's model was that it forced scientists to reconsider the relationship between certainty and probability in the physical world. Classical physics, inherited from Newton and refined by Maxwell, was built on the idea that if you know enough about a system, you can predict its behavior with perfect accuracy. But the atom refused to obey this doctrine. Electrons did not glide smoothly through space on predictable paths. They occupied specific energy levels, made sudden transitions, and behaved in ways that defied deterministic laws. Bohr's introduction of quantization was the first step toward a world where certainty would be replaced by probability, and where nature's behavior could only be described in terms of likelihood rather than exact outcomes. This shift in thinking was not easy for the scientific community to accept. Even Einstein, who admired Bohr's intelligence and respected the clarity of his model, struggled to embrace the idea that nature could be fundamentally uncertain. His famous remark, "God does not play dice," reflected his discomfort with the probabilistic nature of quantum theory. But Bohr responded with equal conviction, insisting that the quantum world did not conform to human expectations. It followed its own rules, and those rules were revealed through experimental evidence. Bohr believed that embracing uncertainty was not a weakness, but a necessary step toward understanding the true structure of reality. Bohr's atomic model didn't just work for hydrogen, it inspired physicists to explore how quantization shaped more complex atoms. While the simple circular orbits of the early model would eventually evolve into Schrödinger's wave functions and orbital shapes, Bohr's central idea, that electrons could occupy only specific energy states, remained an unshakable foundation. This concept became the backbone of quantum chemistry, explaining why elements behave differently, why chemical bonds form, and why the periodic table displays its characteristic patterns. Every element's personality, its reactivity, its bonding behavior, its role in the natural world, could now be traced back to the quantum structure first revealed by Bohr. This understanding opened the door to practical applications that would transform the 20th century and beyond. The discovery of lasers, the development of semiconductors, the entire field of electronics, and even the birth of quantum computing owe their origins to the realization that energy is quantized. None of these technologies would exist without Bohr's leap of imagination. His model showed that electrons could jump between energy levels by absorbing or emitting precise amounts of energy. This simple rule eventually led to the engineering of devices that manipulate electrons with incredible precision, powering the digital age and shaping the world in ways Bohr could never have imagined. Yet Bohr's revolution went far deeper than technology. It reshaped the philosophical foundation of science itself. The classical worldview imagined a universe governed by absolute laws, independent of observers. But Bohr's quantum model hinted that the act of observation mattered. Electrons did not reveal their behavior until measured. Their states, energies, and transitions were intertwined with the instruments and interactions used to detect them. This idea challenged centuries of scientific tradition and forced humanity to rethink what it meant to know something about nature. Bohr's philosophical reflections culminated in one of his most influential ideas, complementarity. This principle stated that certain properties of quantum systems, such as wave-like behavior and particle-like behavior, could not be observed simultaneously. They were complementary aspects of the same reality, each revealed only under specific conditions. Although complementarity would later be formalized in the broader framework of quantum mechanics, its roots can be traced back to Bohr's early work on the atom and his recognition that quantum systems defy classical categories. His interpretation of quantum mechanics, often referred to as the Copenhagen interpretation, did not arise in a single moment, but evolved through years of deep thought, debate, and collaboration. It was grounded in Bohr's belief that the quantum world could not be described using classical terms alone. Instead, new concepts were required, concepts that acknowledged the role of the observer and the fundamental limits on what could be known. This interpretation became one of the central pillars of modern physics, shaping how generations of scientists think about the nature of reality. The importance of Bohr's atomic model also lay in the scientific culture it helped create. At the Institute for Theoretical Physics in Copenhagen, which Bohr founded, physicists from around the world gathered to discuss, debate, and explore the emerging world of quantum theory. This place became the intellectual home of the quantum revolution. Young scientists such as Werner Heisenberg, Wolfgang Pauli, and Max Born worked alongside Bohr, inspired by his insight and guided by his philosophy. The conversations that unfolded within those walls shaped the very direction of quantum mechanics. It was not just a building, it was a birthplace of ideas that transformed science. Bohr's influence extended beyond physics. His willingness to embrace ambiguity, his belief in the interconnectedness of systems, and his philosophical openness resonated with thinkers in fields ranging from biology to psychology. He saw patterns in nature that transcended discipline, linking the behavior of atoms to broader questions about knowledge, meaning, and human understanding. His work demonstrated that science was not just a search for facts, but a journey toward deeper insight about the natural world and our place within it. As the decades passed, the full impact of Bohr's quantum model became increasingly clear. It laid the foundation for nuclear physics, enabling scientists to explore the structure of the nucleus and the processes that power stars. It guided the development of quantum field theory, which describes the interactions of particles at the most fundamental level. It shaped the study of materials, leading to breakthroughs in superconductivity, magnetism, and condensed matter physics. Everywhere scientists looked, the fingerprints of Bohr's breakthrough were visible. Even today, more than a century after Bohr introduced his atomic model, the scientific world continues to build upon the principles he established. Quantum computers, which promise to revolutionize computing by harnessing the power of superposition and entanglement, are direct descendants of the quantum ideas Bohr helped bring into existence. Quantum cryptography, quantum sensing, and quantum communication, all cutting-edge fields, trace their origins back to the moment Bohr dared to imagine the atom as something more complex, more dynamic, and more mysterious than any classical system could describe. Perhaps the most remarkable aspect of Bohr's contribution is that it opened a doorway into a world that remains rich with unanswered questions. The quantum world is still a realm of deep mystery, where particles exist in states that defy intuition, and where the very fabric of reality seems to shift depending on how it is examined. Bohr's model did not provide all the answers, but it provided the first coherent framework for asking the right questions. It gave humanity a map, not of the entire quantum landscape, but of the path that leads into it. The story of Bohr's quantum model is ultimately a story of human courage in the pursuit of truth. It shows how one idea, grounded in observation yet reaching beyond tradition, can change the course of history. Bohr's willingness to follow the evidence, even when it led into strange and unfamiliar territory, embodies the spirit of scientific discovery at its highest form. His model transformed the atom from a source of confusion into a gateway to understanding the universe at its most fundamental level. As scientists continue to explore the quantum world, they walk in Bohr's footsteps, guided by the principles he uncovered and the questions he raised. Every new discovery, from quantum entanglement to particle-wave duality, echoes the revolution he began. His legacy is woven into the physics of every laboratory, every experiment, and every theory that seeks to explain the mysteries of matter and energy. In the end, Bohr's introduction of the quantum model of the atom stands as one of the great milestones in human thought. It reshaped the scientific worldview, illuminated the hidden structure of nature, and laid the foundation for a technological era that continues to evolve. Through his work, Bohr revealed that the universe is not a static, mechanical construct but a dynamic, ever-changing tapestry governed by quantum laws, and in that revelation, he offered humanity a new way to see the world, not through the lens of certainty and predictability, but through the deeper, more profound understanding that the heart of reality beats in quantum rhythms. Bohr's vision remains alive in every field that touches the quantum realm, from physics to engineering, from cosmology to computation. His bold idea continues to inspire future generations of scientists to push beyond the boundaries of the known, to question assumptions, and to explore the infinite possibilities hidden within the smallest building blocks of nature. What began as a quest to understand the atom became a revolution that shaped modern physics, transformed technology, and expanded the horizons of human knowledge. And as long as the pursuit of understanding continues, Bohr's legacy will endure, guiding the next steps into the ever-deepening mystery of the quantum universe. At the dawn of the 20th century, the atom stood as a paradox. Scientists had glimpsed its structure through experiments, yet its behavior defied classical expectations. Electrons, tiny charged particles orbiting a dense nucleus, were supposed to lose energy as they revolved, radiating electromagnetic waves according to Maxwell's classical theory. If classical mechanics were correct, electrons would have spiraled inward, colliding with the nucleus in an infinitesimal fraction of a second. Matter, as humans understood it, should not have existed. And yet, here we were, solid, tangible, enduring objects stable and resistant to collapse. It was a mystery that demanded explanation, a riddle that classical physics could not solve, and it was in this scientific void that Niels Bohr found his calling. Bohr approached the atom not merely as a collection of particles, but as a dynamic, structured system with rules that transcended classical physics. He realized that understanding atomic stability required a radical departure from conventional thinking. The laws of motion and electromagnetism, which had served humanity for centuries, were insufficient. At the microscopic scale, nature played by a different set of rules. The classical view, elegant in its simplicity, failed to account for the remarkable persistence of atoms. Bohr's genius was to recognize that the solution was not incremental adjustment, but a fundamental reconceptualization of atomic behavior. The breakthrough came when Bohr combined empirical evidence with audacious theoretical insight. Hydrogen's spectral lines, meticulously recorded by experimenters, held a secret code of the atom's structure. Each bright line of the emission spectrum corresponded to a distinct energy release, a photon of a specific frequency. Bohr understood that these lines were not random, they were evidence of discrete energy levels within the atom. Unlike a planet that can orbit at any distance, electrons were constrained to specific quantized orbits, each with a fixed energy. In these orbits, electrons did not radiate energy, and thus the atom remained stable. The mystery of atomic endurance was solved by the radical notion that electrons were not free to spiral continuously inward. They were confined to stable zones dictated by nature itself. Bohr's model was revolutionary not only for what it explained, but for how it reframed our understanding of energy and motion at the atomic scale. In classical physics, motion was continuous, energy could vary smoothly, and changes occurred gradually. Bohr's electron orbits shattered this assumption. Energy levels were discrete, and electrons could move from one level to another only by absorbing or emitting a precise quantum of energy. These abrupt transitions, were known as quantum jumps, were foreign to classical intuition, yet they perfectly accounted for the stability of atoms. By confining electrons to specific energy levels, Bohr created a mechanism for atomic endurance, demonstrating that the collapse predicted by classical theory was not a flaw of observation, but a flaw of assumption. The implications of this realization were profound. For the first time, stability in the microscopic world could be explained in a way that aligned with observable reality. Electrons were no longer bound to decay into the nucleus. The very architecture of the atom imposed order and structure. The quantization of energy created invisible scaffolding, a series of stepping stones that allowed electrons to orbit indefinitely without radiating away energy. In this framework, the atom was not fragile or unstable, but a carefully orchestrated system of discrete, balanced forces. Bohr's insight transformed the atom from a theoretical problem into a coherent, predictable entity, laying the foundation for all subsequent advances in quantum physics. Bohr's contribution extended beyond the simple idea of fixed orbits. It challenged scientists to think differently about the interaction between electrons and the nucleus. Classical physics had assumed that electrons were small charges responding to electric forces in a continuous way. Yet Bohr demonstrated that the stability of the atom depended on constraints that had no classical analog. Electrons were tethered to their orbits not by an arbitrary law, but by fundamental quantum principles. This tethering was absolute, only certain energies were permitted, and the atom remained resilient against collapse. By introducing this quantum rule, Bohr not only explained atomic stability, but also revealed the underlying logic of nature at the smallest scales. The elegance of Bohr's explanation lay in its simplicity and predictive power. Using his model, he could calculate the energy differences between electron orbits, and these calculations matched the observed spectral lines of hydrogen with remarkable precision. The atom, once an abstract and unstable notion, became a system governed by mathematical order. Every spectral line, every photon emitted, was a direct reflection of an electron transitioning between stable states. Bohr had transformed chaos into clarity, providing not just answers but a method to understand and predict atomic behavior. Stability was no longer a mystery. It was a natural consequence of the rules he had discovered. Bohr's insights also illuminated the relationship between microscopic and macroscopic phenomena. The stability of atoms explained why matter occupies space, why chemical elements maintain their identities, and why the macroscopic world behaves reliably. The solidity of a chair, the persistence of a stone, the very existence of matter, all traced back to the rules Bohr uncovered. Without electron stability, molecules could not form, chemical reactions could not occur predictably, and the universe as we know it would be a volatile, collapsing chaos. Bohr had not only solved a scientific problem, he had provided the key to understanding the persistent, ordered structure of reality itself. The broader scientific community quickly recognized the importance of Bohr's model. It offered an explanatory framework that bridged observation and theory, experiment and prediction. Classical physics could no longer account for the enduring stability of the atom. Bohr's quantum rules provided the first truly coherent explanation. The model demonstrated that electrons were fundamentally different from any macroscopic object, obeying laws that were subtle, discrete, and probabilistic. It set a precedent for a new kind of physics, one that embraced counterintuitive principles and focused on the patterns revealed by nature rather than the assumptions inherited from classical mechanics. Bohr's approach also embodied a philosophical shift in understanding the universe. The atom's stability was not merely a mechanical phenomenon, but a quantum phenomenon. Electrons could exist indefinitely without energy loss because nature had imposed constraints that defied classical logic. Stability was not a default property, it was an emergent feature of the quantum rules that governed electron behavior. Bohr's vision showed that the universe, at its most fundamental level, was ordered in ways that could not be deduced from common experience. That logic and intuition drawn from the macroscopic world were insufficient to explain the microscopic world. This recognition of atomic stability influenced generations of scientists. Bohr's model became the foundation upon which the structure of matter, chemical bonding, and spectroscopy were built. It inspired the development of quantum mechanics, the work of Schrödinger, Heisenberg, and Dirac, and even shaped early nuclear physics. By explaining why electrons do not collapse into the nucleus, Bohr solved a problem that had threatened to undermine all of atomic theory. His model provided a solid platform for exploring the atom's deeper mysteries, from the behavior of electrons in multi-electron atoms to the interactions that drive nuclear forces. Bohr's insight was not only theoretical, it aligned perfectly with experiment. The spectral lines of hydrogen, the simplest atom, could be predicted with astonishing accuracy using his quantized orbits. Observers saw light emitted at exact wavelengths, and Bohr's theory explained why. The atom was stable because electrons occupied precise energy states, moving only when absorbing or emitting discrete quanta. Each calculation, each correspondence with experiment, reinforced the validity of his revolutionary approach. Stability was no longer a mystery, it was an observable, measurable, and predictable phenomenon. Moreover, the explanation of atomic stability reshaped the understanding of chemical phenomena. Electrons in stable orbits determined how atoms bond, how molecules form, and how reactions unfold. The stability of electrons around a nucleus became the foundation for understanding the behavior of all elements. Bohr's model connected the microscopic world of quantum mechanics with the macroscopic world of chemistry and biology. Stability was no longer an abstract concept, it had direct implications for the observable universe, influencing the very processes that sustain life and shape the physical world. Bohr's work on atomic stability also challenged and inspired philosophical debates about the nature of reality. Classical determinism, the idea that every event could be predicted with perfect accuracy, was incompatible with quantum rules. Electrons existed in defined orbits, yet their transitions occurred as sudden jumps. Nature, it seemed, was structured yet inherently discontinuous at the smallest scales. Bohr's explanation of stability revealed that order did not require continuous motion or classical predictability. Stability was an emergent property arising from the discrete, quantum architecture of the atom. In conclusion, Bohr's explanation of atomic stability was more than a scientific achievement, it was a paradigm shift. By showing why electrons do not collapse into the nucleus, he resolved a contradiction that had puzzled physicists for decades. He revealed that the atom is a carefully balanced system of quantized energy levels, that electrons are confined to stable orbits, and that the persistence of matter is a direct consequence of quantum rules. The insights he provided continue to influence every field of science, from physics and chemistry to materials science and quantum technology. Bohr's vision illuminated the invisible scaffolding of nature, proving that the stability of matter is not accidental, but an intrinsic property of the quantum universe. The deeper one delves into the significance of atomic stability, the more remarkable Bohr's achievement becomes. What seems intuitive today, the notion that electrons remain in fixed orbits around the nucleus, is actually a profound insight born from confronting nature's deepest contradictions. Classical physics predicted collapse, yet the universe persisted. Bohr's genius lay in seeing that the persistence of matter was not accidental, but a consequence of a new principle, that electrons occupy discrete energy levels. This principle transformed the understanding of the atom from an unstable, theoretical abstraction into a reliable, predictable system. The atom, once a source of confusion and paradox, became a window into the ordered, quantized framework of reality. Bohr's model also redefined the relationship between energy and motion. In classical mechanics, energy is a continuous quantity, flowing smoothly and gradually. But in the quantum world, energy is delivered in distinct, indivisible packets. Electrons can move from one orbit to another only by absorbing or emitting a quantum of energy precisely equal to the difference between levels. This concept, while strange to intuition, elegantly explained why electrons remain in stable orbits. They do not radiate energy continuously because their allowed states are inherently discrete. These rules ensure that the atom retains its structure and does not collapse, providing the foundation for the observable stability of all matter. In essence, Bohr replaced the idea of continuous motion with a quantum framework, demonstrating that nature enforces stability through discrete rules. The success of Bohr's theory lay not only in its explanation of stability, but also in its predictive power. Spectroscopic studies had long revealed that hydrogen emitted light in distinct lines, but no existing theory could account for the pattern. Bohr's model explained these spectral lines as the result of electrons transitioning between quantized orbits. Each transition corresponded to a photon of a precise energy, producing the characteristic lines observed in experiments. The fact that Bohr could predict these lines with remarkable accuracy validated his theory and showed that atomic stability was not an abstract principle but a tangible, observable phenomenon. His model bridged the gap between theory and experiment in a way that no classical approach could, proving that stability was an intrinsic feature of the atom's quantum architecture. Bohr's insight also had profound implications for the structure of matter itself. Stable electron orbits allowed atoms to maintain their identities over time, ensuring that chemical properties remained consistent. This stability explained why elements exhibit characteristic behaviors and why compounds form predictable patterns. The periodic table, once a catalog of elements based on empirical observation, now had a theoretical underpinning. The arrangement of electrons in quantized orbits explained chemical reactivity, bonding tendencies, and the fundamental rules governing molecular interactions. Bohr's model showed that stability at the atomic level underpins the entire observable universe, connecting the microscopic quantum world to the macroscopic phenomena we experience every day. The philosophical impact of Bohr's explanation of stability cannot be overstated. Classical physics assumed determinism. If one knew the forces acting on a system, one could predict its future precisely. Bohr's model revealed that determinism was not violated in the classical sense, but had to be reinterpreted in the context of quantum constraints. Electrons followed strict rules dictated by energy quantization, and while their positions and motions could not be predicted continuously, their allowed states were sharply defined. Stability, therefore, was not random, it was structured, ordered, and governed by fundamental quantum laws. Bohr's insight challenged long-held assumptions about predictability and causality, ushering in a new era of scientific thought. The model also highlighted the interplay between experimental observation and theoretical insight. Bohr's quantized orbits were inspired by empirical evidence from spectroscopy and the observed stability of matter. Yet the conceptual leap to discrete energy levels required imagination, creativity, and a willingness to depart from classical assumptions. By combining rigorous mathematics with philosophical openness, Bohr created a framework that not only explained existing observations but also guided future research. His theory became the touchstone for subsequent discoveries in quantum mechanics, serving as a template for understanding more complex atomic systems and the interactions that govern chemical and physical phenomena. Furthermore, Bohr's explanation of atomic stability influenced the development of nuclear physics. Understanding that electrons remain in fixed orbits around the nucleus provided a clearer picture of the forces acting at the atomic core. While the nucleus itself would later become the focus of investigation, Bohr's work laid the groundwork by establishing the rules governing the surrounding electron cloud. The stability of this cloud became crucial in interpreting nuclear behavior, decay processes, and atomic interactions. His insights created a bridge between atomic physics and the emerging field of nuclear science, highlighting the centrality of electron stability in the broader architecture of matter. Bohr's model also inspired technological innovation. The recognition that energy is quantized and that electrons occupy stable states allowed scientists to manipulate atomic behavior with precision. Devices like lasers, semiconductors, and atomic clocks rely on transitions between energy levels that Bohr first described. Modern electronics, quantum computing, and advanced imaging techniques all trace their origins back to his explanation of atomic stability. In this sense, Bohr's theoretical insight has had tangible effects far beyond the laboratory, shaping the tools, technologies, and infrastructure of the modern world. The stability of atoms, as explained by Bohr, also provided a framework for understanding chemical bonding and molecular structures. Electrons in stable orbits could interact predictably with electrons in other atoms, forming bonds that were consistent and reliable. This understanding allowed chemists to move from empirical rules to theoretical models, predicting molecular geometry, bond strength, and reaction pathways. The persistence and reliability of matter, rooted in electron stability, became a cornerstone of chemical theory, connecting quantum physics with the observable properties of substances in the macroscopic world. Bohr's work also reshaped the conceptualization of energy itself. By demonstrating that electrons could absorb or emit discrete quanta of energy without destabilizing the atom, he introduced a fundamentally new understanding of how energy operates at microscopic scales. Energy was no longer a smooth continuum, but a series of steps, each corresponding to a permitted transition. This realization challenged assumptions about conservation and transfer, providing a foundation for later developments in quantum mechanics, including wave-particle duality and uncertainty principles. Stability in this context was not merely physical but conceptual, redefining the way scientists thought about energy in the quantum domain. The clarity and elegance of Bohr's model allowed it to endure despite its initial limitations. While later refinements introduced the concepts of electron clouds, wave functions, and more complex orbital shapes, the fundamental principle of discrete energy levels remains intact. The stability of electrons around the nucleus continues to be understood through the lens of quantized states, and every modern application of quantum theory owes a debt to Bohr's pioneering insight. His explanation of why electrons do not collapse into the nucleus remains a cornerstone of scientific education, experimental interpretation, and theoretical modeling. Beyond physics and chemistry, Bohr's concept of stability influenced broader scientific and philosophical thinking. It challenged notions of continuity and predictability, showing that nature can be orderly and resilient even when governed by counterintuitive rules. It illustrated that stability is not an inherent property of matter, but a result of specific structural and energetic constraints. By demonstrating that electrons occupy stable states, Bohr revealed a fundamental principle that underlies the reliability of the observable universe. This insight has implications for how scientists think about complexity, emergence, and the relationship between microscopic rules and macroscopic phenomena. Bohr's explanation of atomic stability also fostered collaboration and debate within the scientific community. The Institute for Theoretical Physics in Copenhagen became a hub where young physicists gathered to explore the implications of quantized orbits. Discussions, debates, and thought experiments extended the understanding of atomic behavior, inspired new generations of researchers, and laid the foundation for the formal development of quantum mechanics. Bohr's model was not only a solution, but also an invitation to further inquiry, a starting point for exploring the profound and intricate laws that govern the microscopic world. In the context of modern science, Bohr's insight into atomic stability continues to resonate. Understanding that electrons occupy specific energy levels underlies the principles of spectroscopy, quantum chemistry, solid-state physics, and even astrophysics. The behavior of matter under extreme conditions, the formation of stars and planets, and the development of advanced materials all depend on the same foundational rules that Bohr elucidated. Atomic stability is not an isolated concept, but a guiding principle that informs countless areas of research, from fundamental theory to practical application. Ultimately, Bohr's explanation of why electrons do not collapse into the nucleus represents a triumph of human imagination, logic, and observation. He confronted a problem that classical physics could not solve, dared to propose a radical new model, and provided a framework that explained the enduring stability of matter. His insight revealed the elegant order underlying the microscopic world and illuminated the rules that make the macroscopic world possible. The atom, once a source of paradox and confusion, became a well-understood and predictable system thanks to Bohr's vision. Bohr's work on atomic stability is a testament to the power of intellectual courage. By challenging classical assumptions and embracing the strange principles of the quantum world, he reshaped not only physics but the very way humanity understands the universe. Stability, as he explained it, is the natural outcome of quantum laws, a property emerging from discrete energy levels and structured electron behavior. This insight continues to guide scientists, inform technological innovation, and inspire philosophical reflection, confirming that Bohr's contribution to understanding atomic stability is both timeless and foundational. In every atom, in every molecule, and in every chemical reaction, the echoes of Bohr's insight are present. Electrons remain steadfast in their quantized orbits, ensuring the persistence and reliability of matter. The universe, as we know it, depends on the very principles he uncovered. By explaining atomic stability, Bohr not only solved a profound scientific mystery, but also provided a lens through which to view the order, resilience, and beauty of the natural world. His legacy endures in the enduring stability of matter itself, a reminder that even the smallest particles follow rules of breathtaking elegance and profound consequence. The discovery of atomic spectral lines was one of the most puzzling phenomena in early 20th century physics. When scientists observed hydrogen gas, they noticed that it did not emit a continuous spectrum of light, as one might expect from classical theories of radiation. Instead, it produced bright, distinct lines at precise wavelengths, like a hidden code etched into the very fabric of the atom. These lines were not arbitrary, they formed a regular pattern that hinted at an underlying order, yet no explanation existed that could reconcile them with the laws of classical physics. The mystery of spectral lines had eluded the brightest minds of the era, leaving a profound question. Why did atoms emit light only in these discrete bands? It was this enigma that Niels Bohr set out to unravel, and in doing so, he transformed the understanding of the atomic world. Bohr approached the problem with the insight that the atom was not a simple mechanical system. Classical physics, with its continuous orbits and smoothly varying energies, could not account for the precise lines observed in spectra. In a classical atom, electrons should radiate energy continuously as they move, producing a smeared, unbroken spectrum of light. But this was not what experiments showed. The lines were sharp, fixed, and repeatable. They indicated that electrons were not radiating energy randomly or continuously. Rather, they were transitioning between specific energy states, each jump corresponding to a single line in the spectrum. Bohr recognized that these lines were the footprints of quantized energy, the first direct evidence that energy at the atomic scale was not continuous but discrete. The brilliance of Bohr's model lay in its ability to connect these spectral lines with the structure of the atom. He proposed that electrons could occupy only certain allowed orbits, each with a defined energy. When an electron absorbed energy, it could jump to a higher orbit. When it fell back to a lower orbit, it emitted a photon, a discrete packet of light, with energy equal to the difference between the two levels. This simple principle explained the mystery that had baffled physicists. Each spectral line corresponded to a quantum leap between specific orbits. The atom was not a passive object, but an active emitter of light, revealing its inner structure in discrete flashes that could be measured and studied. Hydrogen, the simplest atom, became the proving ground for Bohr's ideas. Its spectral lines, already catalogued meticulously by experimentalists such as Balmer, had resisted theoretical explanation for decades. Bohr's model provided a mathematical framework that reproduced these lines with astonishing precision. Using his quantized orbits and the concept of energy levels, he could calculate the wavelengths of emitted photons, and these calculations matched the observed spectral lines exactly. For the first time, theory and experiment were in harmony. The spectral lines were no longer a mysterious puzzle, they were direct manifestations of the atom's internal quantum structure. The implications of this discovery were profound. Bohr's explanation demonstrated that light itself is intimately connected to the discrete nature of matter. The energy emitted or absorbed by electrons was not arbitrary but quantized, revealing a fundamental order in the atomic world. This realization bridged the gap between the observable universe and the unseen microscopic processes. Light, once thought of as a continuous wave in classical theory, became a messenger of quantum transitions, carrying information about the atom's internal architecture. Each spectral line was a testament to the precision and predictability of quantum mechanics, a signal from the invisible world that could be measured, calculated, and understood. Bohr's insight also challenged traditional notions of energy and motion. Electrons, rather than moving continuously and radiating energy at all times, were confined to stable orbits where they did not emit radiation. Only when they changed orbits did they emit or absorb energy, and this energy came in discrete units or quanta. The atom became a structured system of possibilities, each electron limited to specific states and each transition producing a distinct, measurable effect. Spectroscopy, the study of these lines, thus became a powerful tool for probing atomic structure, revealing details about energy levels, electron arrangements, and the interactions between charged particles and light. Bohr had transformed spectroscopy from an observational curiosity into a window into the quantum world. This discovery also reshaped the philosophical understanding of nature. Classical physics assumed continuity changes occurred smoothly, energy flowed seamlessly, and motion was predictable. Bohr's model showed that, at the atomic scale, reality is governed by rules that defy this intuition. Energy exists in discrete packets, motion occurs in sudden jumps, and light is emitted only in quantized bursts. The sharp spectral lines were evidence that the universe is ordered not through smooth gradations, but through distinct, structured transitions. Bohr had revealed a hidden layer of reality, one where the fundamental processes of matter and energy follow laws that are precise, discrete, and deeply counterintuitive. The success of Bohr's model in explaining spectral lines also validated the emerging concept of quantum theory. Max Planck's earlier work on quantized energy in blackbody radiation had introduced the idea that energy is not continuous, but it was Bohr who applied this concept directly to the atom. By linking energy quantization to observable spectral lines, he provided concrete proof that quantum principles govern the structure of matter. Spectroscopy became both a testing ground and a source of confirmation for the new physics. Experiments could verify theoretical predictions with remarkable accuracy, establishing confidence in a framework that would come to dominate 20th-century physics. Bohr's explanation of spectral lines went beyond mere numbers. it introduced a conceptual revolution. Electrons were no longer thought of as tiny particles moving freely in a void. They were now bound by quantized orbits, participating in a precise dance that dictated when and how energy could be emitted. Each spectral line was like a musical note in a cosmic symphony, a signature of the atom's inner harmony. Light, as it streamed from hydrogen gas or other elements, carried a message encoded by quantum rules. Bohr had discovered the language of the atom, a language that could be read, interpreted, and ultimately used to explore the hidden structure of matter. Moreover, Bohr's insights into spectral lines had far-reaching applications. By understanding the discrete nature of atomic emissions, scientists could identify elements in distant stars, analyze the composition of unknown substances, and even probe the early universe. Spectroscopy became a cornerstone of astrophysics and chemistry, linking laboratory experiments to cosmic observations. The sharp lines in a star's spectrum, once mysterious, could now be interpreted in terms of electron transitions, energy quantization, and the principles Bohr had unveiled. The explanation of spectral lines thus connected the microcosm of the atom to the macrocosm of the universe, showing that quantum principles are not confined to the laboratory but operate on cosmic scales as well. The clarity provided by Bohr's model also allowed for the refinement of other atomic theories. While his early model applied most directly to hydrogen, it set the stage for understanding more complex atoms. Multi-electron systems could be analyzed using the principles of quantized energy and electron transitions, leading to the development of more sophisticated models that incorporated electron spin, orbital shapes, and magnetic interactions. Spectroscopy remained a guiding tool, with spectral lines providing empirical validation for increasingly advanced theoretical frameworks. Bohr's initial explanation of the hydrogen spectrum became the blueprint for understanding the behavior of all elements, demonstrating the universal applicability of his quantum insights. The impact of Bohr's work on spectral lines extended into technological innovation as well. Understanding that atoms emit light in discrete quanta laid the groundwork for lasers, photonics, and quantum optics. Devices that manipulate electrons and photons rely on the principles first revealed in Bohr's atomic model. The ability to control light emission and absorption at precise energy levels is central to modern electronics, communication, and measurement technologies. Bohr's explanation of spectral lines thus bridged the gap between abstract theory and practical application, showing that understanding fundamental principles of nature can lead directly to transformative technological advancements. In addition to its practical significance, Bohr's explanation also reshaped the narrative of scientific discovery itself. It demonstrated the power of integrating theoretical reasoning with experimental observation. Bohr did not invent spectral lines, he interpreted them. He saw patterns where others saw confusion, drew conclusions from precise measurements, and created a theoretical framework that explained and predicted phenomena. His approach exemplified the scientific method at its most elegant. Careful observation combined with imaginative reasoning, guided by the principle that nature operates according to discoverable laws, however counterintuitive they may appear. As the scientific community absorbed Bohr's insights, the explanation of spectral lines became a cornerstone of education and research. Students learned to see light not as a continuous wave, but as a messenger of quantum transitions, each photon carrying information about the structure of the atom. Spectroscopy laboratories around the world adopted Bohr's principles, using spectral lines to identify elements, study chemical reactions, and explore the energy structure of matter. His model transformed a long-standing mystery into a practical tool for inquiry, demonstrating that even the most subtle observations can reveal profound truths about the universe. Finally, Bohr's work highlighted the interconnectedness of scientific progress. Planck's quantization of energy, Einstein's photon theory of light, and experimental spectroscopy all converged in Bohr's atomic model. By decoding the spectral lines, Bohr created a unifying framework that linked previously disparate ideas, showing that quantum principles govern both the emission of light and the stability of matter. His explanation was not merely a solution to a puzzle. It was a synthesis of the emerging understanding of quantum reality, one that would shape the development of modern physics for generations. Bohr's explanation of spectral lines was not merely an academic exercise, it represented a profound shift in the way scientists perceived the interaction between matter and light. In classical theory, light was considered a continuous wave, and energy emission from atoms was expected to occur in a smooth, uninterrupted fashion. Yet the experimental evidence of discrete spectral lines contradicted this expectation. Bohr's insight revealed that energy is inherently quantized. Atoms release or absorb energy only in precise packets, and these quantized interactions manifest as the sharp lines observed in spectra. This realization fundamentally altered the conceptual framework of physics, showing that the quantum world is structured, ordered, and governed by rules that are at once subtle and precise. The discrete nature of spectral lines also revealed a hidden symmetry within the atom. Each line corresponds to a transition between two specific energy levels, and these levels are arranged in a manner that is not arbitrary but follows a mathematical pattern. In hydrogen, for instance, the Balmer series of lines can be predicted accurately using Bohr's formulas, demonstrating that the atom's internal structure imposes strict constraints on the behavior of electrons. This orderliness suggested that the atom is more than a collection of particles, it is a system governed by deep, underlying principles. Every photon emitted carries information about the electron's transition, providing a direct link between observed phenomena and the internal architecture of the atom. Bohr's model also revealed the limitations of classical mechanics. In a classical picture, electrons moving in orbits should radiate energy continuously, causing them to spiral into the nucleus and destroy the atom. This catastrophic collapse never occurs, and spectral lines provided concrete evidence that the classical view was insufficient. Bohr demonstrated that by restricting electrons to discrete energy levels, the atom could remain stable and still emit energy in a manner consistent with observation. The quantization of energy reconciled the apparent paradox between atomic stability and the emission of light, showing that nature follows principles that classical reasoning cannot anticipate. The implications extended far beyond the hydrogen atom. While Bohr's original calculations applied most directly to simple systems, the concept of quantized energy levels became central to understanding more complex atoms. Spectroscopy allowed scientists to study heavier elements, revealing patterns in their emission lines that echoed the principles first observed in hydrogen. Bohr's approach provided a framework for predicting the energy levels of multi-electron atoms, even if additional refinements were required to account for electron interactions. The universality of quantized transitions demonstrated that the principles underlying spectral lines were fundamental, not incidental, revealing a profound coherence in the natural world. Bohr's explanation also had profound consequences for the understanding of light itself. Photons, once a theoretical construct proposed by Einstein to explain the photoelectric effect, were now directly linked to observable phenomena in atomic spectra. Each spectral line corresponds to a photon with a specific energy, and the wavelength of the emitted light can be calculated from the difference between electron energy levels. This connection between matter and light reinforced the dual nature of energy. It is both a property of the atom and a traveling quantum of radiation. By decoding spectral lines, Bohr provided one of the earliest concrete demonstrations of the quantum nature of both electrons and photons, laying the groundwork for the development of quantum electrodynamics. The methodology Bohr employed was as significant as the results themselves. He combined careful analysis of experimental data with bold theoretical assumptions, introducing postulates that departed radically from classical physics. His recognition that energy levels are quantized, that electrons do not radiate while in stable orbits, and that transitions between orbits produce discrete quanta of light were conceptual leaps that required both imagination and rigor. By linking these postulates to observable spectral lines, Bohr validated his theory and provided a model that could be tested, refined, and extended. The scientific method, in its most elegant form, was exemplified in Bohr's approach: observation-inspired theory. Theory predicted phenomena, and predictions were confirmed through experiment. Bohr's work on spectral lines also paved the way for the development of modern atomic theory. The sharp lines in hydrogen's spectrum hinted at the discrete nature of quantum states, inspiring subsequent advances such as Schrödinger's wave mechanics and Heisenberg's matrix mechanics. These frameworks built upon Bohr's insights, generalizing the principles of quantization and electron transitions to all atoms. Spectroscopy became a crucial tool for probing atomic and molecular structures, with applications ranging from fundamental physics to chemistry, astronomy, and materials science. The patterns revealed in spectral lines provided a roadmap for understanding the behavior of electrons, energy transfer, and the organization of matter at its most fundamental level. One of the most striking consequences of Bohr's explanation was its universality. Spectral lines were not anomalies or peculiarities, they were manifestations of a deeper law governing all atoms. As scientists examined other elements, they observed series of discrete lines analogous to those in hydrogen, each corresponding to quantized electron transitions. Bohr's principle, that electrons occupy specific energy levels and emit or absorb photons during transitions, provided a unifying explanation for these patterns. This universality reinforced the idea that quantization is a fundamental feature of nature, shaping not only atomic behavior but the very structure of matter. The technological implications of spectral line analysis are equally profound. Understanding the discrete nature of electron transitions led directly to the development of devices such as lasers, which rely on controlled emission of photons at specific energies. Atomic clocks, spectroscopy instruments, and quantum sensors all operate based on the principles first articulated by Bohr. By explaining the origin of spectral lines, he provided a foundation for technologies that manipulate and measure light and energy with unparalleled precision. The impact of this work extends from laboratory science to everyday applications, demonstrating the profound practical significance of theoretical insight. Bohr's explanation of spectral lines also deepened the philosophical understanding of the quantum world. It demonstrated that nature operates according to discrete, well-defined rules at the microscopic scale, even when these rules contradict classical expectations. Light emission is no longer continuous, it occurs in quantized bursts. Electrons are no longer free particles, they occupy defined energy states. The universe at its most fundamental level is structured, ordered, and intelligible, but it is intelligible in ways that challenge intuition. Spectral lines provide a visible and measurable signature of this underlying order, showing that even phenomena as seemingly simple as the color of emitted light are governed by profound quantum principles. The study of spectral lines also influenced the understanding of chemical reactions and molecular behavior. The energies associated with electron transitions determine how atoms interact, bond, and form compounds. By analyzing the spectra of molecules, scientists can infer bond energies, molecular geometries, and chemical dynamics. Bohr's insight into the quantized nature of atomic transitions thus extended from physics into chemistry, establishing a foundation for quantum chemistry and molecular spectroscopy. Spectral lines became more than lines of light. They became a language through which the microscopic behavior of matter could be read, interpreted, and understood. Another important consequence of Bohr's work was the connection it established between theory and observation. Prior to his model, spectral lines were empirical observations without theoretical explanation. Bohr's model transformed them into predictable consequences of quantum rules. By calculating energy differences between orbits, he could predict the wavelengths of emitted light. This predictive power was unprecedented, turning spectroscopy from an empirical science into a theoretical tool that could probe the structure of atoms with accuracy and precision. The atom was no longer mysterious. Its internal workings could be inferred from the light it emitted, demonstrating the deep interplay between theory and experiment. Bohr's insights into spectral lines also inspired new ways of thinking about energy transfer and interaction between matter and radiation. Electrons in quantized states do not absorb or emit energy continuously, but only during specific transitions. This principle underlies the operation of countless modern technologies, from lasers to solar cells, from atomic clocks to quantum computing. By decoding the mechanism behind spectral lines, Bohr revealed the rules that govern energy flow at the quantum scale, showing that even the behavior of light is intimately connected to the structure of matter. Finally, Bohr's explanation of spectral lines reinforced the emerging vision of quantum mechanics as a coherent framework for understanding the microscopic world. The sharp lines observed in hydrogen and other elements were not anomalies, but evidence of a deeper order, one that would guide the development of wave mechanics, matrix mechanics, and quantum field theory. Spectral lines provided tangible proof that energy is quantized, that electrons occupy defined states, and that transitions between these states produce observable effects. Bohr's work thus connected the abstract principles of quantum theory with measurable phenomena, laying the foundation for a century of discovery, innovation, and technological progress. The most revolutionary aspect of Bohr's work was his daring introduction of quantization to explain the behavior of electrons in atoms. At a time when classical physics dominated scientific thought, the idea that energy could exist only in discrete amounts seemed almost heretical. Yet Bohr recognized that nature at the atomic scale did not conform to classical expectations. Electrons did not orbit freely like planets around a sun. They were confined to specific energy levels, and their transitions between these levels were governed by precise, quantized rules. This insight transformed the study of the microscopic world, creating a bridge between observable phenomena, such as spectral lines, and the underlying principles that govern matter and energy. Bohr's quantization was not merely a mathematical convenience. It was a statement about the fundamental structure of reality. By introducing the concept of quantized energy levels, Bohr provided a framework that could explain why atoms are stable, why they emit light in discrete spectra, and why matter itself does not collapse. Classical physics, with its continuous motion and energy, could not account for these observations. Electrons confined to quantized orbits avoided radiating energy continuously, maintaining the integrity of the atom. When they moved between levels, they emitted or absorbed energy in precise packets, known as quanta. This principle, simple in concept yet profound in consequence, became the cornerstone of what would later be formalized as quantum mechanics. It showed that at the microscopic level, the universe operates according to rules that are fundamentally different from those of the macroscopic world. Bohr's quantization also laid the foundation for understanding the dual nature of matter and energy. Light, electrons, and other particles do not behave purely as waves or particles. Their behavior is constrained by quantized states. By linking energy quantization to observable transitions, Bohr provided the first clear evidence that the discrete structure of energy is a natural law, not a theoretical abstraction. This principle guided subsequent developments in quantum mechanics, including Heisenberg's matrix mechanics and Schrödinger's wave equations. Every modern theory of atomic and subatomic behavior builds upon the insight that energy is not continuous but exists in discrete levels, a truth first articulated in Bohr's model. The impact of Bohr's quantization extended beyond physics into chemistry, materials science, and technology. Chemical bonding, molecular structure, and the periodic properties of elements can all be understood through the lens of quantized energy levels. Electrons occupy specific states that dictate how atoms interact, form bonds, and create stable molecules. In technology, the principles of quantization underpin semiconductors, lasers, quantum computing, and countless devices that manipulate light and energy at precise scales. Bohr's insight transformed not only theoretical understanding, but also practical applications, demonstrating that foundational scientific ideas can reshape the physical world. Furthermore, Bohr's introduction of quantization challenged scientists to rethink the nature of reality itself. It forced a departure from the deterministic, continuous worldview of classical physics and opened the door to a probabilistic understanding of matter and energy. Electrons do not move along arbitrary paths, they occupy well-defined states, and the transitions between these states follow strict rules. This perspective revolutionized the philosophy of science, showing that the universe is ordered yet fundamentally governed by principles that defy everyday intuition. Quantization became the lens through which physicists could interpret phenomena at the smallest scales, providing clarity in a realm that had long seemed chaotic and inaccessible. Bohr's work thus represents a turning point in human understanding. By introducing quantization, he created the foundation for modern quantum mechanics, bridging theory and observation, mathematics and experiment, and abstract principles and real-world applications. His insight revealed that the microscopic world is structured, predictable, and deeply ordered, yet fundamentally different from the classical universe. Every modern exploration of atoms, molecules, and subatomic particles rests upon this principle. Bohr's quantization was not merely a theoretical innovation, it was a paradigm shift that reshaped the trajectory of science, philosophy, and technology, leaving an enduring legacy that continues to define our understanding of the quantum world. One of Bohr's most profound contributions to modern physics was his formulation of the correspondence principle, a concept that elegantly bridged the gap between the familiar world of classical physics and the strange, counterintuitive realm of quantum mechanics. While Bohr's quantized orbits explained the behavior of electrons and spectral lines, he recognized the importance of connecting these novel quantum ideas to the well-established laws of classical physics in situations where they overlap. The correspondence principle posited that, in the limit of large quantum numbers, the predictions of quantum theory should converge with those of classical physics. In essence, it provided continuity between the old and the new, ensuring that quantum mechanics was not an isolated framework but a natural extension of centuries of scientific understanding. The principle itself offered a guiding methodology for interpreting phenomena that straddle the boundary between the microscopic and macroscopic worlds. While quantum mechanics governs the behavior of atoms and subatomic particles, classical mechanics still accurately describes planetary motion, electrical circuits, and the motion of everyday objects. Bohr's correspondence principle assured scientists that these two domains were not contradictory, but complementary. Quantum laws dominate where energy levels are discrete and interactions occur at atomic scales, whereas classical laws emerge as approximations in the macroscopic world. This insight provided a conceptual map, enabling physicists to translate between the abstract quantum realm and the tangible classical world, a task critical for both theoretical development and experimental design. By introducing the correspondence principle, Bohr also offered a means to validate quantum theory. Early quantum models faced skepticism because they defied conventional intuition and classical expectations. The correspondence principle reassured scientists that quantum predictions would reproduce familiar results when applied to systems with high quantum numbers or large-scale behavior. For example, in highly excited atoms where electrons occupy large orbits, the emitted radiation begins to resemble classical electromagnetic waves. This alignment between quantum predictions and classical behavior served as a powerful check on the validity of Bohr's theory, reinforcing confidence in a framework that otherwise seemed radical and untested. The correspondence principle also played a pivotal role in shaping the future development of quantum mechanics. By establishing a conceptual link between classical and quantum descriptions, it provided a roadmap for subsequent physicists exploring more complex atomic systems. It guided the formulation of new mathematical tools, such as wave mechanics and matrix mechanics, by showing how classical concepts could emerge from quantum foundations. This bridging function ensured that quantum theory remained connected to empirical reality while expanding the frontiers of understanding. The principle became a cornerstone of the theoretical architecture, demonstrating that new scientific paradigms could build upon and coexist with existing knowledge rather than discarding it entirely. Moreover, Bohr's insight had profound philosophical implications. It highlighted the layered nature of physical law, showing that seemingly disparate phenomena are governed by a continuum of principles that operate at different scales. Classical mechanics is not wrong. It is a limit of a more general quantum theory, applicable where discrete energy differences are negligible. This realization challenged traditional notions of absolute correctness in science, emphasizing instead the contextual nature of physical laws. It also underscored the importance of seeking unifying principles, guiding future generations of scientists to look for connections between phenomena rather than treating each domain as entirely separate. The practical impact of the correspondence principle extended to experimental and technological innovation as well. It allowed scientists to interpret atomic spectra, radiation emission, and other quantum phenomena in ways that aligned with classical intuition when appropriate, facilitating measurements, calculations, and predictions. This continuity made the abstract world of quantum physics more accessible, providing a framework for designing experiments and interpreting results that would otherwise appear inexplicable. It served as a bridge not only between theories, but between the theoretical and experimental practice of physics, enabling rapid advances in understanding and application. Ultimately, Bohr's correspondence principle exemplifies the subtlety and foresight of his scientific vision. By connecting the emerging quantum framework with classical physics, he created a guiding principle that ensured consistency, continuity, and coherence across the scales of nature. It allowed quantum mechanics to grow from an audacious hypothesis into a robust, predictive, and deeply insightful theory. The principle influenced not only the development of atomic theory, but also the philosophical and methodological foundations of modern science, demonstrating that progress often comes from harmonizing the new with the established. Through the correspondence principle, Bohr left an enduring legacy, a conceptual bridge spanning the divide between the tangible world of classical mechanics and the enigmatic depths of quantum reality. Bohr's most striking achievement was his ability to transform abstract theoretical insights into concrete, testable predictions, particularly regarding atomic spectra. Before his intervention, the spectral lines of elements like hydrogen were meticulously cataloged, yet no model could account for their precise positions or patterns. They were mysteries that teased the curiosity of physicists, revealing order without explanation. Bohr's genius lay in recognizing that these patterns were not arbitrary, but the fingerprints of discrete energy transitions within atoms. By introducing quantized electron orbits and relating the energy differences between these orbits to the emission or absorption of light, he created a framework capable of predicting the exact wavelengths of spectral lines. This ability to predict rather than merely describe transformed the study of atomic physics, giving scientists a tool that bridged theory and observation with unprecedented accuracy. The predictive power of Bohr's model had immediate experimental implications. Spectroscopy, the study of the interaction between matter and light, became not just a method of observation but a means of validating theory. When hydrogen's emission lines were measured and compared with Bohr's calculations, the agreement was remarkable. Each line corresponded precisely to a predicted electron transition, confirming that the atom's structure was ordered and quantized. This empirical validation was revolutionary because it provided tangible evidence for a model that otherwise might have seemed speculative. By linking theoretical constructs to measurable phenomena, Bohr demonstrated the essential interplay between theory and experiment in modern physics. Moreover, Bohr's predictive framework extended beyond hydrogen. While his initial model applied most directly to simple, single-electron atoms, it established principles that guided the study of more complex elements. By analyzing spectral lines of multi-electron atoms, scientists could infer electron arrangements, energy level structures, and patterns of chemical behavior. Bohr's approach turned the atom from an abstract concept into a system whose behavior could be anticipated and systematically studied. Experimentalists could now design observations with the confidence that quantum theory provided a roadmap, ensuring that spectroscopy was no longer merely descriptive, but explanatory and predictive. The framework also clarified the relationship between light and matter in ways that had profound scientific consequences. Each spectral line represented a discrete quantum of energy emitted or absorbed during an electron transition. This not only explained why spectral lines are sharp and fixed, but also connected the emission of light to fundamental atomic structure. Photons were no longer mysterious, continuous waves. They were precise messengers of quantized energy exchanges. This understanding laid the groundwork for later developments in quantum electrodynamics and the study of photon-matter interactions, revealing that even light itself could be described through the principles articulated in Bohr's atomic model. Bohr's predictive power extended to chemical and physical phenomena as well. Knowledge of atomic spectra enabled scientists to identify elements in stars and distant astronomical objects, analyze chemical reactions at the molecular level, and study energy transitions in materials. The ability to anticipate spectral lines transformed spectroscopy into a universal tool, providing insights across physics, chemistry, and astronomy. In this sense, Bohr's work demonstrated that a theory capable of making precise predictions does more than explain existing data. It empowers the discovery of new phenomena, guiding researchers to insights that might otherwise remain hidden. The success of Bohr's predictive framework also inspired confidence in quantum principles more broadly. At a time when classical mechanics could not account for atomic behavior, Bohr showed that quantization was not merely a theoretical abstraction, but a principle that could generate precise, verifiable predictions. This validated the nascent field of quantum theory, encouraging other physicists to explore and expand upon its ideas. The predictive accuracy of his model became a benchmark, demonstrating that even counterintuitive, non-classical concepts could yield measurable, consistent results. Finally, Bohr's model exemplified the scientific ideal of theory guiding experiment. By predicting spectral lines, he transformed the atom from an enigmatic entity into a system whose behavior could be quantified, studied, and anticipated. This predictive capacity solidified the atom's place as a foundation for modern physics and chemistry. It demonstrated that rigorous theoretical reasoning, when combined with empirical observation, could unlock the deepest mysteries of nature. Through his predictive framework for atomic spectra, Bohr not only revolutionized experimental physics, but also established a lasting paradigm for the interplay between theory, measurement, and discovery in the quantum world. The influence of Bohr's vision extended far beyond the immediate explanations of atomic structure, spectral lines, and quantization. His model became a beacon for the next generation of physicists, demonstrating that bold theoretical insight, grounded in careful observation, could unravel the deepest mysteries of the natural world. By introducing quantized orbits, discrete energy levels, and the correspondence principle, Bohr created a framework that challenged classical thinking and opened the door to an entirely new way of understanding matter and energy. Young scientists across Europe and the world recognized that the classical models they had relied upon for decades were insufficient, and Bohr's revolutionary ideas provided both inspiration and a roadmap for exploring the quantum realm. Bohr's work served as a catalyst for collaboration and intellectual exchange, particularly at his Institute for Theoretical Physics in Copenhagen. It became a hub where physicists from diverse backgrounds gathered to discuss, debate, and expand upon the principles he had introduced. Here, the seeds of modern quantum mechanics were nurtured. Figures like Werner Heisenberg, Wolfgang Pauli, and Erwin Schrödinger absorbed Bohr's insights and used them as the foundation for their own groundbreaking contributions. The concept that energy is quantized, that electrons occupy specific orbits, and that atomic behavior can be predicted with mathematical precision became a shared language, uniting a generation of physicists around a common set of principles and a common vision for the future of science. Beyond inspiring individual scientists, Bohr's vision shaped the trajectory of entire fields. Quantum mechanics, which today forms the backbone of modern physics, owes its foundations to the insights he articulated. The principles of quantization, electron transitions, and the correspondence principle provided the scaffolding upon which the formal theories of wave mechanics and matrix mechanics were constructed. Bohr's emphasis on the interplay between theory and experiment encouraged physicists to continually test, refine, and expand their models, fostering a dynamic and iterative process of discovery. The result was a new scientific paradigm, one capable of explaining phenomena that had previously seemed paradoxical or inaccessible. Bohr's influence also extended into technological innovation. The understanding of atomic structure and quantum transitions enabled the development of devices and systems that rely on precise control of energy at microscopic scales. Lasers, semiconductors, atomic clocks, and modern electronics all trace their conceptual roots to the principles he introduced. By revealing the predictable, quantized nature of energy and electron behavior, Bohr provided the foundational knowledge that engineers and physicists could exploit, turning theoretical insights into practical tools that have transformed modern life. His work demonstrated that deep theoretical understanding is not merely an intellectual exercise, but a driver of tangible technological progress. Philosophically, Bohr's vision reshaped the way humanity understands the universe. He showed that the microscopic world operates under rules that defy classical intuition, yet these rules are precise, consistent, and discoverable. Reality is not chaotic at the atomic scale, it is structured according to principles that govern stability, energy, and interaction. Bohr's emphasis on quantization, the correspondence principle, and predictive modeling illustrated that even phenomena invisible to the naked eye could be understood, measured, and harnessed. This perspective challenged conventional assumptions, expanded the horizons of scientific thought, and inspired a generation to explore nature with both rigor and imagination. The enduring legacy of Bohr's vision is also evident in education and research. Students and scholars worldwide continue to study his model, learning to think in terms of quantized energy levels, electron transitions, and atomic spectra. His work provides a conceptual foundation for understanding quantum mechanics, chemistry, astrophysics, and materials science. By inspiring curiosity, guiding experimental exploration, and providing a framework for theoretical innovation, Bohr ensured that his ideas would resonate for generations. His vision created a lineage of discovery, a chain of intellectual pursuit that continues to expand our understanding of the quantum world. Ultimately, Bohr's vision demonstrated the power of combining imaginative theoretical insight with empirical rigor. He transformed atomic physics from a field of speculation into a precise, predictive science, laying the groundwork for both modern quantum mechanics and technological advancement. His ideas inspired countless physicists to question assumptions, explore new possibilities, and build upon his legacy. In shaping the intellectual landscape of the 20th century and beyond, Bohr not only explained the atom, but also illuminated a path for humanity to understand, harness, and innovate within the quantum universe. His contributions continue to resonate, proving that the vision of a single pioneering mind can alter the course of science, technology, and human knowledge forever.